Pleased to be back here, and it's always fun to come and talk to such an audience about some of the work that we're doing in my group at UT. And this time I was given the task of summarizing two somewhat different areas in 30 minutes. So I'm going to go through, I think, explain some of the key ideas in these two different topics here. So I'm going to start off with a bit of an introduction to where I see connected and aerial vehicles going. So it's UAVs plus connectivity. And so I'm going to present some slides that were developed by my colleague, Dr. Noya Gonzalez-Prelchik, as part of our center's efforts to get more into aerial platforms. So we have a lot of research now on wireless for vehicles, but those vehicles have primarily been cars on the ground. And we're now looking at ways to go into the air. And so this is essentially part of that pitch. So the story starts here with, every good pitch has a hockey stick curve, right? And this is it here. So essentially the commercial drone industry is about at this inflection point where we're going to start to see potentially this exponential growth in revenue. And it's going to lead to more jobs and, of course, taxes as well. And there are projections that the commercial drone fleets are going to go from what was about, let's say, 50,000 right now to maybe 500,000 in 2021. And I'm not talking here about the hobbyists and consumers as well. This is just for commercial applications. And then these are some predictions that everything here is referenced on this link here on some of the states predicted to see a lot of jobs in terms of the drone activities here. And we're fortunate to be in Texas, which is one of those states that's been identified as potential for drone. And basically, the economic impact here is really big. And I don't think we're tapping into this now because there's just not many commercial applications. I mean, the places you see drones right now, you see hobbyists, there's drone racing, there's photography, and then there's, of course, the many military applications. And then a few in the industry, particularly related to cinematography. But there's not yet so many drones flying around conducting commercial services as there could be. So here's like a summary of the main disruptive applications. So we have umbrella control, flower monitoring and watering, pet walking. Yeah, okay, this was a joke here. These were, some of the, I would say, disruptive, some of the more crazy ideas for drones that maybe is not here yet, and we probably don't need 5G for it, to be fair. Although the pet walking, I don't know, I've seen in my neighborhood several times, there's this sort of Uber for walking dogs, and so I see this guy there walking like 10 dogs at the same time, and so maybe he would be interested. I don't know. So I'm going to tell you about now some of the more serious applications for drones, or what we call UAVs, unmanned aerial vehicles here. And one of the main ones is really just as an imaging sensor. One of the primary and the first applications of UAVs in the hands of consumers was to take a camera into the air. And then once you have it into the air, you can fly around and you can get a bird's eye view of all sorts of intriguing things. And the beauty of this is you can do this at a much lower cost than it would take to rent a helicopter and fly it around. So, which would be, in the 500 an hour plus range. So, and this is one of the first places you see this being used is Triad, Zillow, real estate agents. People are hiring commercial drone pilots to come and get aerial view of their lot. And you see this for a lot of times these very large houses like that with a pool, but you see it for almost anything now. And then that creates, it's a really nice selling point there. And then there's also been a lot of interest in having drones that can participate in terms of sporting activities. And so, for example, you want to get photos of someone surfing. I mean, the way that you could do that before was you get out there in the water in a wetsuit and, you got the camera, or you're on the beach with a huge telescopic lens. And so now there's the possibility to actually fly out and get coverage. And then there's companies that have been developing technologies for automatic following, where you're a surfer, you get your wetsuit on, you get your board, you tell the drone, okay, let's go. You go into the water and the drone is, smart enough to come follow you and ideally get those perfect, pipeline kind of shots. So So that's imaging here. And then in this case here, here the aerial platform is really just a way to use a camera. And you don't need necessarily high bandwidth wireless communication, because primarily the sensor and potentially the data storage is on the camera and it's just being flown around. Now, if you had wireless, though, could be attractive, because if you're shooting a movie, you want to be able to see the view that the drone is getting in real time. And so there are applications of the sensing, but that's the main thing I see. And then the control, you need low latency, but you don't need a very high bandwidth just to steer the drone around. Another area is sensing and monitoring. So we've had some discussion about agriculture during lunch. So drones become very good platforms for going out into the field and surveying. And when you combine the different kinds of sensors on there, I mean, you could have different sorts of cameras or other devices, and you can monitor the plants and then apply computer vision algorithms, machine learning, to monitor the growth and make recommendations on, wow, these plants aren't getting enough water, we need to strategically water more over here. And all of this can be done potentially in an automated way. There's work done with drones being used in forestry, monitoring deforestation. So drones maybe will be making periodic sweeps of different areas to look for loggers that shouldn't be there. Traffic monitoring, a lot of the traffic work that happens right now, if you don't have fixed cameras in a place, and in the city of Austin, there's about, I think the number was around 70 cameras. Most of the roads are not dynamically monitored. And so when they need to collect data to figure out if they need to retime lights, the city of Austin or TxDOT, depending on the road, will potentially send someone out with a clicker and a notepad to write what's happening in the cars going by. Or they put that pneumatic strip across the road, which is automatically counting cars, but they don't have a very good way of doing building a dynamic model of the traffic at a particular place. And drones could do that potentially very easily. I mean, you could imagine a fleet of drones flies out, monitors a different part of Austin each day for the purpose of building statistics so that they can optimize the roadways better. That's good for us because right now most of the traffic lights are retimed roughly every 2 years. And if you think about how fast the traffic is growing in Austin, that's insane. So that's an interesting application. And then there's even power line and pipeline monitoring. I'm a private pilot and I don't have an airplane, and sometimes I'm looking in online to see, what airplane can I get and how cheap can it be. And you see these like Cessnas and like 172 classic trainer airplane, it's like 25K, which is really cheap. And then you read the fine print, and you're like, this thing has 14,000 hours. Where the hell did they get those hours? And then you read in there, and this was one of those pipeline aircraft. And so there's little airplanes that are, like anywhere there's an oil pipeline exposed, they're just flying along the whole day, just looking to make sure it's not leaking. And that's a job for a pilot. I'm not sure it's an interesting job, but it's a job. And so a drone could easily do that, and combined again with computer vision type algorithms could be looking for leaks in a way that doesn't require having the airplane, maintaining it, paying the pilot, paying for fuel, et cetera here. So another application is transportation and delivery. I'm really excited about this one. There are about 100 companies right now developing aircraft like what's seen there, which are capable of vertical takeoff and landing. Most of them are electric powered, and almost all of them are built around a consumer drone type configuration, usually not a quadcopter because you don't have enough redundancy, typically octocopter. I didn't count the number of rotors there. It looks like more than that there. And we have such a company that's a research project at UT. It's in stealth mode that's developing that kind of a technology here. And this is really exciting. I mean, when you think about, maybe this is not the solution for me to get from UT to the conference. That's only 2 miles. I think one of those beautiful scooters is a better option. But if I want to get over here to LBJ, which is about a 45-mile trip away, that's an hour slog, and you could do that in 10 minutes. So there's some interesting disruption that's happening in the ability of these drones to have large and carry 1 to 4 people. And there's also the package deliveries. There's a lot of excitement about this in the Amazon world about UAVs delivering smaller payloads. It could be pizza, burrito, letters, and that seems a little bit far-fetched, but there are a lot of situations where people are carrying these small objects around, and the UAV could do it with without much activity, not getting caught up in the roadway congestion. That's pretty cool. And then finally, the wireless connection here is that, all the things I talked about before, they could be done where, the UAV could be operating autonomously, or they could be remotely controlled, or you could be doing something more with the sensors and on the platform there. And so a lot of different things that can be done with wireless. I mean, the UAV itself can act as one of those, as a mobile base station. And so it could connect back to a non-mobile base station through, for example, millimeter wave, and then it could be deployed for hotspot coverage. Like when they have ACL in town at Zilker Park, ringed around the park, there's a whole bunch of portable base stations that are set up. So you could have some base stations that are flying out there over the park. Of course, the obvious question then is, why is there not some guy with a gun shooting the base station down, falling into the people? I don't know. That's an interesting set of challenges there on its own. Maybe you don't fly over the people, fly over the non-occupied area. There are many applications in these disaster settings where the wired infrastructure breaks down and you need to have connectivity with people that are in the disaster as well as the emergency workers there. And so you could imagine like a multi-hop network with one or more aerial nodes that are able to communicate with people on the ground. And then there's also these doing things. One of the ones I've seen that's pretty interesting is drive testing. And I think this was actually T-Mobile, and they were flying around a rather conventional drone with 2 phones, and they were driving it over at the racetrack here in Austin to configure the cellular network for the track. And so drive testing is where you drive around and you measure the signal strength, and then you can go back and tweak the base station a little bit. You can tweak the down tilt, maybe adjust the power. And the drive testing was being done just by flying a phone around. So I thought that was pretty cool. So these are some of the new applications that are coming here. And so there's a lot of opportunity for technology development, and this is why my group is looking at these sorts of applications. So one of the things is that many of these applications require that the drone can be flown in what's called non-line of sight. So right now, primarily when you're flying a drone, like if you buy one, you go fly it, you have to be able to see it at all times. This is the law right now. But all the interesting applications, like seeing what your neighbor's doing, in his backyard, you need to be able to fly probably without your line of sight, so you can sneak up and see what's happening over there, right? So those things require good wireless control, but also very good localization. You want to make sure you can avoid a tree, and you know where the tree is, you have to know where the drone is so that you can avoid it. So positioning is really important, and there's also the related topics of mapping and navigation. So the way that automated cars work, most of them build a 3D map of the environment and then use that map to localize themselves in the environment, identify objects that have not been mapped, for example, one of these crazy scooters, and then plan the trajectory in that environment there. And UAVs can be used for the mapping, but that in itself, technology is also important. There's collaborative sensing where the sensors are fused from different UAVs. So in the agricultural setting, the UAVs are monitoring different parts of the field, but maybe what's happening in one part of the field is affecting the other. If this one here is not getting water, maybe that's because there's a leak and this other part's getting too much water. So collaborative sensing is involving fusing all the sensor data together, processing it, and making inferences about that. And then there's also opportunities for 5G, for millimeter wave, for multiple antenna communication. And these are some of the things that we're looking at UT and trying to figure out the role for communication in all of the applications that I showed you there. And I think right now, probably the ones I'm most excited about is the delivery with the small drones, because I think there's a lot of challenge in creating a network where drones from different manufacturers can coexist in the same city without colliding with one another, not to mention endangering people on the ground. You're going to need communication there. You're going to need to be able to coordinate. Just like the stuff we do with automated driving, the drones will have to coordinate with one another, potentially in a dynamic fashion, and then also be able to sense, oh, hey, there's a truck here. I can't fly there. I got to fly over it. But I can't fly over it because someone's coming above me right now. So all of that, I think, is going to be quite interesting. And then these are topics that we're investing in right now. So that's part one of the talk. So part two, I want to wrap up with tell you a little bit about machine learning for communication. So machine learning is a hot topic right now, and I'm sure it's affecting your business as well as mine. And one of the hot areas is called machine learning for communications. And so this is where machine learning algorithms are used to potentially configure a communication link better, or are even used to completely engineer the link itself. I'm more interested in using machine learning to help configure such links. And my first work actually was with Bob Daniels, who mentioned he did his PhD on the topic, built a nice prototype, and developed this technology in 2008, 2009. And it was one of those things, it was kind of before its time. Everyone thought we were a little bit crazy and, didn't get any funding for it. And then it kind of dropped for several years. And then all of a sudden it's back. So I'm working with companies and say, oh, we love what you're doing, but can you put machine learning in the title? So, or even another sponsor that came from an unnamed government agency is like, yeah, okay, we can fund anything you have as long as machine learning is there. So that's pretty interesting. And we need money to pay the students to do the work, it turns out. So I'm going to tell you a little bit about just machine learning and how it's used. We've used it in a couple places here. So there's a lot of different kinds of machine learning algorithms. There's a lot of problems that machine learning can solve. I'm going to explain a little bit about the use of machine learning for classification. And I'm going to talk about here, because this is what we've been using in our research, a problem which is called supervised learning. And the supervised learning problem is that you have a labeled set of data. And in this case, this is a classification. So the data are labeled into different classes. The example I'm going to show you on the next slide, the data are labeled either red or green. And you want to be able to get a new piece of data and figure out, is that red or green? So you just want to classify it. But you want to build the classifier based on past observations. That's it. A conventional signal processing approach, like what we use a lot of times in communications, is that we build a mathematical model of the observation. We say, okay, there's a circuit here. We can model noise as Gaussian. The channel is fading. So we get a received signal that is attenuated due to fading plus Gaussian noise. And then we derive some algorithms based on that model. And machine learning is really data-driven. It just says, okay, you've got inputs and outputs, and then it tries to fit the model to explain that behavior. And then this is like what a typical supervised learning type problem looks like. And this is what's used in the illustration is in a shallow learning configuration where you've got raw data that comes in. This could be, almost anything that you can think of. I mean, if you're on Amazon and you're trying to predict what book someone might like, that incoming data would include maybe my name, my location, my past order history, but it could include all kinds of strange stuff like the strongest color in the book, what was the weight, was it electronic or not? Any possible thing you can think of can go into that input vector. And then what happens in what are called shallow learning methods is that input data is transformed to reduce the amount of data that you need. So for example, maybe the color of the cover of the book doesn't matter. Honestly, I don't know. Maybe it does, in fact. And so the front end is often designed based on experiments and experts' knowledge. So maybe someone comes in who does marketing and says, look, you have a bunch of data, ignore most of that data and focus on these, because that's what's really important. And that dimensionality reduction step is important because the smaller the dimension, the easier it's going to be to train a model. The larger the dimension, the more data you need to train, because the dimensionality of the model is going up actually exponentially in the dimension of the input. And then the second part is what's called the classifier. And this is going to be this mathematical block that takes that truncated input and maps it into the class that we're trying to predict. And so we're going to use the training data, a set of data that's already been labeled, to build that mathematical model, figure out how to pre-process, and then we're going to apply it on some new data. And that's the basic idea of supervised learning. Now, if you are going to take what's called a deep approach, this has been really popular the last few years, convolutional neural networks, autoencoders, a whole bunch of different frameworks. You normally dispense with that piece on the front end and take the raw data, and the network is able to learn how to do that dimensionality reduction as part of its learning at the expense of needing more data. But both of them, the problem they're solving in principle is the same. And the way that we've been, let me explain just briefly here with this example with the classification. So this this is an illustration here, so it's a 2D plot. And I don't know, Bob, did I get this from your dissertation? Yeah, okay. I was just thinking about that. Suspiciously, I forgot to acknowledge Bob here. Yeah. Yeah, that happens after a while. I mean, come on, it's been almost 10 years, so. But yeah, so this figure here, so this shows two classes of data. So there's, the blue ones and the red ones here. And the feature dimension is 2. So whatever input data is processed into something that has 2 real numbers, and those 2 real numbers correspond to coordinates, which are then plotted here, and the point is tagged with its class, which is in this case red or blue. And so what the machine learning algorithm does is the machine learning algorithm devises a rule for separating the 2 different classes of data. And in this case here, it looks pretty clear to all of us that this yellow line is a pretty good match. And look, some of the points are not quite on the line, right? But if you put the line over here, maybe more blue points end up over there. So it's an approximation. But so the machine learning algorithm, in this case, if we were searching for the best line to do the classification, it would search for 2 points, the slope and the intercept of the line, and then find that to optimize some performance metric based on classification. And then a new point would come in and would be compared with this line and then labeled accordingly. So that's a kind of a simplistic example, but that is the principle. It's what's happening here. When you go to higher dimensions, it's harder to visualize. The line might become some sort of a curve or a manifold, and then there's transformations applied to put it back into some picture like this. So the application that, the stuff that Bob did is really cool, and that's described in a keynote talk I have on YouTube. But I wanted to tell you about what we're doing with it these days in millimeter wave. And so in particular, in the vehicular applications of millimeter wave, there's a lot of consistency in how the communication link is working, because the cars are driving on the road, going in the appropriate directions, presumably staying in their own lane. And there's a lot of predictability about how it performs based on what's happening in the environment. So when this car is near the space station, it's usually pointing its beam at the base station. And this is to be contrasted with an application in the nomadic setting where I might be wandering around very slowly, but some of the time I block my signal, some of the time my finger's on the antenna. There's a lot less predictability there about how to configure the link, even though the time scale is slower. So we've been focusing on how to use machine learning to help configure the link in this vehicular setting. And why I like machine learning and why it's proving to be useful beyond a traditional signal processing tool is that it gives us a mathematical framework to incorporate site information. Like you can imagine that the way that you configure the antennas for a vehicle might be different in rush hour and at 3 in the morning when there's no cars on there, or at 5 when the trucks are dropping off beer to restock all of the bars. So that's the time of day. That's an interesting feature. What was the weather like that day? What's the density of traffic? Is there something going on with the people? And then comparing this with similarity with other different places. And so there's a lot of information that could be used as an input into an algorithm to help configure the link better and more reliably, basically with less overhead. And so what we've been looking at here is this problem where we want to point a beam from the base station to the subscriber, which is on a car. And sometimes you want to point the beam directly. And then if you know the coordinates of the base station, you know the coordinates of the car. It's a simple geometry problem to figure out the angle. But what if there's a truck blocking that link? Well, maybe you can get through the truck or under the truck, but maybe you're instead better off reflecting off another car. So some of the time this direct link works, other times this link works, and maybe other times this link works. And so we're using machine learning to learn the most promising sets of alternatives to try, so that instead of trying all the possibilities, which is the standard approach now would be we sweep over, try all these 64 beams here, this guy listens for each 64 beams with its own beam. So it's like trying to point 2 flashlights together. And there's a lot of overhead associated with that. So machine learning is nice because it helps to take all this different kind of input data together and make good predictions. And that's what we've been using it for. One of the first work that we did was using the location of the base station, the location of the car. And so what happened is, a car would come into the network and would try to communicate with the base station on each of these beams with each of its receive beams. So you'd sweep over all the transmit, all the receive beams, and collect all that data. And then another car would come in, you do the same thing, collect the data. So a lot of cars would come in. Let's say you spend a whole day just driving cars through collecting data. You actually don't need a whole day's worth of data. And then you train the algorithm, and then the next day when cars come in, you use information about their position and the kind of car to recommend sets of beams to try. And so this is a recommendation problem. It's like when you go into Netflix, it says, hey, what about these 5 movies? Would you like to try these? And maybe it puts the one that it thinks you like the most first, but it's not just showing you one movie, it's showing you several. Because maybe you're not in the mood to see, I don't know, whatever my favorite one is, involves a lot of eyeball stabbing and blood, all the Danes, all this. Anyways, I like these violent movies the past year or so. And so it's recommending, and the thing about the recommendation is that you don't want to recommend 3 beams that point to the building. If you can only recommend 3, you want to recommend the direct beam, a beam off the building, and a beam that points off of a car. Because the idea is to find one that works, not the 3 that work the best. And so that's at most of the time. So it's like a different problem here. We're trying to optimize this to minimize outage. And so we developed techniques for doing that based on the position of the vehicle. And that's the feature that we exploit. And that's a feature that's not normally exploited in cellular systems. The cellular infrastructure doesn't use an explicit measurement of your position to do its configuration. It might infer your position for things like handoff, but it's not actually turning the GPS on your phone and using that data, which is what we're hypothesizing here. And then the next step of that work was that we were thinking, hey, if all the vehicles are connected, don't I know where the other cars are as well? So I know if that truck is blocking the link because I know where it is and I know it's a truck. So we call this situational awareness. And so then we started developing algorithms that use a map of the environment that's occupied by cars and trucks with different heights. And then the challenge here was figuring out how to take that information and train the machine learning algorithm with it so that we're not left with too much information. And we tried a whole bunch of different approaches. And then the shallow learning approach, what we found was that the features that were important were basically the truck locations because the cars weren't blocking the beam. And then the truck location in the first lane was most important. The second lane was second most. And then the cars in the first and the cars in the second lane. So if you didn't want to use as much data, you might just say, okay, here's the locations of the trucks in the first lane, and that would give pretty good performance. And then a deep learning approach, which we also tried, would translate that situational awareness. Instead of talking about vehicles as a coordinate with a label, truck or car, we just color in a pixel that corresponds to if that space on the road is occupied. So this is a map that I made from that image there. And then this image would be input into a deep network and used to predict one or multiple beams that work. And why this is formatted in an image, the main reason is that there are many deep machine learning algorithms that have been successful on image processing problems. And so there's a lot of mathematical and software machinery to solve those problems. And so if you can take your problem and make an image, that solves the practical implementation of that quite a bit. So that's what we did here, and we tried and compared all these different approaches. By the way, our hand-engineered approach was better than the best deep learning approach we could find. Not that you can't do better there, but there's so much hype about deep learning, but deep learning doesn't replace the knowledge of a good engineer. So that's some of the work we did. This is, this is like an illustration here of what's happening. So, by using the learning, we're able to predict the beam without overhead. And since we spend less of the time trying to find a good beam, the rates that we get are better than if we just point the beam between the transmitter and receiver. So this is not capturing the overhead. This is just showing that, when the line of sight is blocked, our approach gives better performance because we find a good non-line of sight path. And then this was just examples. We studied a lot of different approaches, but the main thing we found is that knowing where the trucks were that are closest to the base station, that was the main thing that was important. So further away trucks in our lane, those didn't matter. And the performance in terms of alignment increased with just really knowing a few of the strongest trucks. So that was an interesting result. And then the other thing, where we're going now is trying to imagine a cellular network where there is more than just a base station antenna on the tower. There's other kinds of sensors. There's maybe there's radar, the LiDAR. You could have cameras. And these are all working together to provide situational awareness information for the vehicles, which are engaged in different levels of automation. The base station is a great place to put sensors. It's high up. It's not blocked by the truck. So you can see all the things in the environment, just like air traffic control tower is high up, not so that it's closer to the planes, but so it can see the planes on the ground and help them navigate. So putting the sensors on the base station makes a lot of sense. Also makes sense for the aerial vehicle application as well, because now we can use the sensors to also detect vehicles in the air, authorized or not, and help them navigate as well. And then we've been using this information to configure the wireless link even better. This is not a functionality that's supported in 5G right now. But for example, if we have radar on the base station, we are tracking the car, we're getting its position. Now we don't need to ask where the cars are. We just use our radar to figure out where cars are, and then we can try those cars instead of trying beams in all directions. That's just an example. I mean, maybe that doesn't quite fit in the 5G setup, but that's an example of how we can use site information to configure the link. And machine learning is helping us do that because we're having difficulty formulating precise mathematical models that capture what's going on, and machine learning just helps us figure out how that information is correlated together. So I'll wrap up here with just a summary. I mean, machine learning now is being used to solve basically every possible problem that you can think of in every possible location. So I don't know, everyone here probably has an example of that. But I mean, communications, people are looking at it to say, hey, instead of OFDM, what if machine learning designed a waveform for me? Ooh, what would happen there? Or instead of using QAM modulation, what if OFDM finds the points of my constellation? Every possible thing you can think of. I mean, people are now trying to do that. And some of the work has been able to come up with machine learning-based designs that are the same or a little bit better than our previous best engineered designs. But these are all for very special cases that aren't totally practical yet. But that's coming. People are looking at machine learning quite a bit in the network. It was already being used in the context of self-organized networks. It's being used for network detection, mobility management, all sorts of different things. So that's it here. So basically, aerial vehicles, interesting set of opportunities. We're going to see more and more in the air for commercial applications in the next 5 years. Machine learning, it's a hammer that's being used to nail every possible thing, nails, screws, rabbits, whatever included, anything. And it's going to impact, all of our businesses. I mean, if the computer can do what I can do, then what do we need me for, right? But it's having a lot of impact. But that said, we shouldn't neglect all of the expert knowledge that we have acquired in the field. And I think there's a lot of opportunities still to put back that information into the algorithms so that they work better. And that's it. Thank you.